What I want to show you in this video is how mathematics is really born out of abstraction of real life situations. The key part of what defines mathematics is abstraction, not having to deal with concrete entities but only the relationships between entities. So you already have an idea of red, right? But red doesn't exactly exist by itself in real life. You can have a red car or a red brick or a red book, but you won't find an example of antique red in a museum because it's not an object. But you can look at all of these objects in terms of their collective redness, and you get an idea for what red really is. Even when it's not attached to anything, you abstracted the idea of color away. This gives you a lot of power to think about things like colors that don't literally have to be things. Red, something that's really an adjective, can be used as a noun because your brain has this power of abstraction. Now, numbers are the same way. If I have one car and I bring in two more cars, I'll have three cars. Although to someone else this might have looked more like four wheels plus eight more wheels. But what if we use the word car to identify the thing in question? Then, as long as the other person understands this language, we have no problem. However, if I was to say car in Chinese, we might be back to the same issue. So I take out my Chinese dictionary, we find the translation of car in English, and then we solve the problem. The key to maths is that we first have to define what a symbol is, and once we have done that, we either know what it means, or look up the symbol to see what it represents, and then apply it to the real world. For instance, the number 3 is basically a symbol we have adopted to mean this many of a certain object, and does not represent any concrete entity, but it represents a relationship between entities. Same thing with bringing together two people, pencils, whatever. We see that this oneness and two-ness behave the same way no matter what the actual thing is that we're talking about. One of blank brought together with two of blank gives three blank. The blank doesn't really matter, so we choose to ignore it. We deal with the one and the two by themselves because we see the common pattern and recognize that the particular object doesn't change what's going on. In the real world, the numbers are always attached to something, but as far as the mathematical rules are concerned, that doesn't matter. This is a very powerful idea and is key to a lot of math. And this mentality is at the base of a lot of math ideas. We have a system that works, and we say, what do we have here that's unnecessary baggage? Or what are the key parts that we're actually trying to do to these things? So we find out what these are and generalize. Addition, let's say, has a few basic properties. A big one is that 3 plus 5 equals 5 plus 3. So the order doesn't matter. Another thing is that we have a 0, so that 0 plus a number equals that same number, no matter what the number is. Again, this is abstraction. We can compile a list of these simple properties and prove various facts about addition from them. Is it pointless? Well, maybe. After all, we already know these are true, right? But the idea is that we can find something else that obeys these rules and go, oh wow, we can model this thing just like adding numbers together. And you do this all the time without even thinking about it. After all, all we've shown so far is that you can add collections of objects. But what's to stop you being able to add distances or angles? Because these other things obey the same basic rules that numbers do, so we can just slap numbers onto them and find something else that works. Now, things that don't follow the rules don't have numbers for them. For example, I can't call putting on my shoes one number and putting on my socks another, because putting on my shoes then my socks is different from putting on my socks then my shoes. They don't behave the right way. And the point is that once we've established the math by itself, once and for all, then we know for sure that it'll always work in a particular application we have for it. This is a very powerful idea that crops up again and again in math and is a large part of the reason why it's so valuable and works so well. Now, to get from this simple abstraction to the crazy maths we have today is simple. Just add some complexity and thousands of years of building upon these accepted rules and definitions, and there you go.